A decision tree is a supervised machine learning algorithm used for classification and regression tasks. It splits data into subsets based on feature values, creating a tree-like structure where each internal node represents a decision based on a feature, each branch represents an outcome, and each leaf node represents a final decision or prediction. Decision trees are easy to interpret, can handle both numerical and categorical data, and are prone to overfitting, which can be mitigated through techniques like pruning or using ensemble methods like random forests. Introduction: Decision trees. Decision trees are a model where we break our data by making decisions using series of conditions, questions. Decision tree algorithm. These are also termed as card algorithms. These are used for classification and regression trees. Decision tree algorithm. These are also termed as card algorithms. These are used for classification and regression trees. Every node yields maximum data in each split, which could be achieved by Ig information gain, Ig. Every node yields maximum data in each split, which could be achieved by Ig information gain, Ig. Root node is split to get maximum info gain. Increase in nodes in the tree causes overfitting. Splitting continues until each of the leaf is pure, one of the possible outcome. Pruning can also be done, which means when splitting a dataset in a decision tree, the goal is to create child nodes that are more homogeneous in terms of the target feature, often referred to as purity. Let's examine the two proposed splits. Split A, parent node, 40 items in feature 1 and 40 items in feature 2. Child 1, 30 items in feature 1 and 10 items in feature 2. Child 2, 10 items in feature 1 and 30 items in feature 2. Split B, parent node, 40 items in feature 1 and 40 items in feature 2. Child 1, 20 items in feature 1 and 40 items in feature 2. Child 2, 20 items in feature 1 and 0 items in feature 2. Comparison: Split A creates child nodes, where each child still contains a mix of both features, although the distribution is uneven. Neither child is completely homogeneous. Split B results in child 2 having only feature 1 items, making it fully homogeneous, pure, regarding feature 2. This split might be preferred because it better separates the data based on the target feature, especially in child 2. Conclusion: when splitting a dataset in a decision tree, the goal is to create child nodes that are more homogeneous in terms of the target feature, often referred to as purity. Let's examine the two proposed splits. Split A is less effective in creating homogeneous groups because both child nodes still have a mix of features. Split B is more effective because it creates a pure child node, child 2, which likely leads to a more meaningful split in the context of decision trees. In decision tree construction, split B would typically be preferred as it more effectively separates the data, which is often measured using metrics like Gini impurity or information gain. Both split A and split B have an equal impurity gain, IgE, of 0.25, meaning both splits reduce the impurity of the dataset equally. However, the choice of the split might depend on further considerations like the simplicity of the tree or the specific distribution of classes in the context of the problem. Gini impurity is a measure of the impurity or diversity of a dataset, used in decision trees to determine the best split. Split A has an information gain of 0.125. Split B has an information gain of 0.17. Split B is better since it results in a higher information gain, indicating a more effective split in reducing impurity. Entropy is a measure of uncertainty or impurity in a dataset, commonly used in decision trees to determine the best split. Split A has an information gain based on entropy of 0.19. Split B has an information gain based on entropy of 0.31. Split B is preferred since it results in a higher information gain, indicating a more effective split in reducing entropy, impurity. Comparison of impurity metrics, scaled. Entropy measures the uncertainty in a dataset, and when scaled, e.g. by dividing by 2, it represents a more moderate level of impurity. Gini index represents an intermediate value of impurity, lying between classification error and entropy. It balances between the extremes, providing a smoother measure of impurity. Classification error represents the simplest form of impurity measurement, capturing only the most frequent classes proportion, often providing a less nuanced view compared to Gini index and entropy. In summary, Gini index is often considered a balanced measure of impurity, with entropy giving a more sensitive measure when scaled, and classification error being the most straightforward but less detailed. Pros: simple to understand, interpret, visualize. It is effective to use in numerical and categorical data outcomes. Requires little effort from users for data preparation. Nonlinear relationships between parameters do not affect tree performance. Able to handle irrelevant attributes, gain equals 0. Cons: may make a complex tree with maximum depth. Unstable, as small variation in input data may result in completely different tree to get generated. As it is a greedy algorithm, may not find globally best tree for a data set. Applications: 1. Business management. 2. Customer relationship management. 3. Fraudulent statement detection. 4. Engineering. 5. Energy consumption. 6. Fault diagnosis. 7. Healthcare management. Here's a complete example of how to use a decision tree classifier in Python with the scikit-learn library and visualize the results using matplotlib. Explanation: import libraries. Matplotlib.pyplot is used for plotting the decision tree. Datasets from sklearn is used to load the iris dataset. Train_test_split is used to split the dataset into training and testing sets. Decision tree classifier is the model we use to create the decision tree. Plot_tree is used to visualize the decision tree. Accuracy_score is used to evaluate the model's performance. Load the dataset. The iris dataset is loaded using datasets.load_iris. It contains features like sepal length, sepal width, petal length, and petal width, along with the target labels representing the species of the iris flower. Split the dataset. The dataset is split into training, 70%, and testing, 30%, sets using train_test_split. This ensures that the model is trained on one part of the data and tested on another to evaluate its performance. Initialize the classifier. A decision tree classifier is initialized with a random seed for reproducibility. Train the model. The classifier is trained using the fit method with the training data, x_train and y_train. Make predictions. The trained model is used to predict the labels for the test set using predict. Calculate accuracy. The accuracy of the model is calculated by comparing the predicted labels with the actual labels from the test set using accuracy_score. Plot the decision tree. The decision tree is visualized using plot_tree, which displays the structure of the tree, including the decision nodes, feature names, class names, and the split criteria. Output. Model accuracy. The printed accuracy gives you an idea of how well the model is performing on the test data. Decision tree plot. A visual representation of the decision tree is shown, illustrating how the model makes decisions based on the features. Each node represents a decision based on one of the input features, and the branches show the outcomes leading to the classification. This code gives a basic overview of how decision trees work, how they can be trained on data, and how they can be visualized to understand their decision-making process.